So first off, I want to thank the organizers and for making this happen, especially in the face of clear challenges. And also Fabio, who gave the preceding talk from zero to deep learning. And was a very useful introduction. And it also was useful for me because I had far too much content in my talk. So I cut out a lot of introductory stuff, and I think that Fabio covered it very well. And also compared to the original description of this talk, I cut out a lot of, I really just whittled it down to the core description of ONNX-Scala. So I also was planning on originally on having an example, like a detailed practical example, and Fabio also did that with his planes on a bridge example. So jumping right into it, I also renamed my talk Typeful Functional Deep Learning Model Inference Plus. Hopefully by the end of the talk, you'll understand everything about that. Let me see. All right, got control of my slides. So about me, you can see that I've been working in this area in the intersection between Scala and machine learning for quite a while. Not always able to use both because the predominant approaches in machine learning are generally wrapped up in Python. But as you can see, this project, ONNX-Scala, is my first project as a primary library author. I've been involved in a lot of other ways in the past. I have a bunch of other repos, but never anything that I've really gone to this degree of issuing releases and writing READMEs for and all of that stuff. So let's jump right into it. ONNX-Scala, the overview. Ultimately, it does what it says on the tin. ONNX, have not yet introduced you to. Scala, I'm sure with this audience, needs no introduction. But essentially, ONNX is a format for representing neural networks. And what it says on the tin with ONNX-Scala is that it will let you load files in that format and evaluate them on examples. Like, for example, if you have an input, which is a picture of a plane, then you want to run inference, which is the same thing as evaluating the graph of the neural network. Started this project 2 years ago, and originally it wasn't able to do that. It wasn't able to actually execute inference on the models because there was no supporting backend for it. So I'll get to that when we get there later. But I started with the parts that are still kind of more experimental, maybe more interesting. It depends on whether you're coming to this from a practical or less practical perspective. And the development on ONNX-Scala, originally for a long time, it was just me with no users that I was aware of. Ultimately, I was doing a contract where we were building on a recommender system, which was pre-existing and not written in any existing deep learning or otherwise machine learning framework, really, custom code. And then we ended up replacing it with a neural recommender, which came from the TensorFlow model zoo. It's under recommendation, you can find it in their repo. But ended up training in TensorFlow, saving it in ONNX, and running it with ONNX-Scala. So that drove some of the development of this project. So deep learning meets functional programming. This is one of the parts where I had a lot more thoughts about this. So really, this is just the top level thing, scratching the surface. If anyone else is interested, I may be giving subsequent talks about this in more detail at Scala Love, possibly at Scalar Online. So deep learning and functional programming really are natural friends, natural allies. In supervised machine learning, model inference, not the training learning part per se, just the inference, is a pure parameterized function. In this description, A is the inputs, what we would normally call the inputs of the neural network. B is the outputs. So in the example that Fabio gave, A is pictures, images of possible planes, and B is a classification of whether they are planes or not. The weights that he was referring to in this case are called parameters, and that's P. So you can see it's a straightforward function. It's a pure function. I'm giving image credit here to one of those interesting papers and things that I'll touch on elsewhere, but it's called Backprop as Functor, which should give you a little hint of the depths that people have gone to in more advanced functional programming and integrating it with deep learning. So that's the first function that we're worried about. The second function that we're generally worried about in machine learning is how do we actually do the training? So then we need an update function where we have the parameters, the inputs, and the outputs. What were the outputs in the inference step? And then what we get back is a new updated set of parameters. Bonus points here. This third one is not actually necessary for an end-to-end machine learning system. But if you want to do this compositionally in a function from a functional perspective, then you need an extra function which, given inputs and outputs and parameters, is going to give you an input which would have been closer to the desired output. So an example of that, going back to Fabio's example, would be if you're given a rainy picture of a plane and it has difficulty discriminating it, then a better example of that would be one with less rain, or in nicer conditions or something like that. So basically we need to generate an input example, maybe not a real training example, but that would be better, so we can pass it backwards, and that enables us to do backpropagation, learn through a whole compositional system. But for now, we're not really worried about learning and training. That's pretty much the end of where I'm going to touch on that in the talk. Because ONNX is all about inference, just running these neural networks. So most approaches to deep learning are imperative/stateful, and they're dynamically/duck typed. So this is the typing thing is due to Python, and the statefulness at lower levels, it's for efficiency reasons, and then also for tradition or ease of use in APIs or things like that. You have stateful things going on there in the APIs generally. So then finally, ONNX meets functional programming. Like I said, it's inference only for now, so we don't need to worry about those second and third functions. And just in case you were concerned that there's something weird going on in ONNX and it's not actually pure or side effect free, it says that in the docs, at least in the master branch. They added the description recently. It says a graph is used to describe a side effect free computation, a function, in the sense that we here mean function. So now let's get to what ONNX actually is. Pretty important if we want to use it. It's open, stands for Open Neural Network Exchange. And the goal is basically to be an intermediate format and enable interoperability between a whole number of mainly Python-based tools and frameworks for deep learning, and it also has support for classical machine learning. So this is not just a fledgling project. It has a certain level of maturity. It's post 1.0. It's, I would say, moving towards 2.0. And it's been donated into the Linux Foundation AI, and it's now a community project, but it is backed by and has consortium members, including all of the big players basically, and many more, dozens more, except for Google. Google is not really on board with ONNX, but you can still use ONNX with TensorFlow. So all of your favorite machine learning tools, or at least deep learning tools, you can export and import in ONNX format. So ONNX, like I said, it's 2 years old. The current version is 1.6. It's got a fair number of contributors. It's got a lot of attention, a lot of stars. It's under active development. As it's getting more mature now, the release cycle is getting slower. And I put a link here to a nice introductory video from Facebook's conference, F8, which will give you a more in-depth overview of what ONNX is. But let's take a look at a neural network represented in ONNX format. This is one of the simplest and oldest forms of neural networks, called a feed-forward neural network, or a multi-layer perceptron. You can see there's a little bit going on here, and for the purposes of this talk, the details are not super important, but it's similar to what Fabio showed in his talk, except that things are broken down into an even more fine-grained level here. So at the top, you have the inputs. Actual input would be a plane, and transpose is where the parameters are feeding in that I was talking about. And we run it all the way down. Sigmoid is the kind of activation function. ReLU is another activation function. There are 2 layers here. And then finally, the output in the plane example would be our classification of this as a plane or not. This particular example I took from PyTorch. The model was defined in PyTorch, which is Facebook's deep learning framework, and one of the most popular, not quite up there in terms of popularity with TensorFlow, but widely used and has a lot of nice features. And I exported it and then visualized it using a nice tool called Netron, which also lets you visualize many, many other kinds of neural networks. and file formats as well. So ONNX is an intermediate representation. You'll notice throughout all of these slides, but particularly this one, I have a lot of links. And in this case, it links to their doc pages for the definitions of all of these things in case anyone's interested. So it's a format for representing neural networks and also a format for representing data, the kind of data you need as input and outputs. So it defines data types, mainly numerical data types, but there also are string and a few other things going on in there, but it's mainly the normal numerical data types that you're used to, float, int, etc. Maybe a bit wider in terms of larger and smaller versions of those than are available in all of our programming languages. It uses protobuf, Google protobuf, to encode and store and transmit tensors. And that's the data, that's the format that we're using to represent the data, both inputs and outputs to the whole network, and also internally data is passed between nodes, generally in the form of tensors, which are multidimensional or n-dimensional arrays. If anyone has ever used Python, in Python, the big thing for this is NumPy, ND array. It also encodes models, and all a model is a graph with some metadata, like which system did you export this from, which version of ONNX were you using, et cetera, et cetera. So really the interesting thing, the meat of this is in the graphs. The graphs are what we were showing right here. This is a visual representation of the graph. And inside the graph, we have nodes. Each one of these boxes here is a node. And each node has inputs and outputs. And you can see that as the lines here. And then also to encode weights, which come in the form of tensors, and attributes, which are other kind of parameters that don't need to be updated in response to learning in the way that the weights do. And then finally, that's all well and good. We can define a graph, but what do each of the nodes mean and what kind of operations are they going to execute? That's the last thing that we need. That's defined in protobuf, again, with operator schemas defined in C++. And the operators are the kind of operations that can be executed. And there are a whole lot of them. But each node has to execute one of these operations, has to embody an operator. So ONNX sits between the training and inference phases of the machine learning model lifecycle. You saw one form of that pipeline or lifecycle again in Fabio's talk. Especially when we look at production deployments of machine learning, and especially more advanced ones, there are a number of reasons why we might want to separate this out. And even though the training systems are definitely capable of doing the inference by necessity, essentially, but there may be a number of different reasons why you might want to use a different system. Like, for example, the training systems might be optimized for ease of use or ability to enable exploratory or experimental development of new networks. They might not be optimized towards performance. You might also want to, for example, run training on GPUs where you have a lot more, data which is sort of static. And then in the real-time use case, you might want to do it on a CPU, and you don't want to batch things necessarily. You might have more of a focus on latency in the inference stage where you're actually doing the classifications on live data. There are a whole wide number of reasons. Specifically in this case, generally Python is going to be used in training, and we're using Scala for inference, which gives us the advantage of integrating with JVM applications and using JVM monitoring tools, and et cetera, et cetera. So there's a whole lot of reasons why this is a good thing. It's also a good thing just for portability. Say you've started developing in one system and you want to be able to move to another one, or you want to have two different teams developing in different systems, and then sort of merging their outputs. Personally, I found a need for this before ONNX even existed. There are other file formats, like PMML is one that Spark ML supports. But Spark's support for it and PMML itself are kind of limited, and it can't really represent a lot of the things that you can represent in ONNX. And it was never designed for neural networks as a focus. And then there's a subsequent proposal called PFA, which is kind of an alternative to this as well, but it has not really gained the adoption and traction, and it doesn't have the institutional backing that ONNX does. Ultimately, this is the best solution we have right now, and it has a lot of development and steam behind it. So, but currently, like I said, it encodes nothing about training. Focus on inference. So when I started developing ONNX-Scala, these are my design goals. I should have even bolded it, but really the main key core thing before we worry about the functional typeful aspects of this is just to make generalized machine learning inference of the kind that you could get from PyTorch or TensorFlow models, make it available in Scala. And like I said, it took a long time to actually reach that part of the goal. But on top of that, since we're in Scala, I wanted to take advantage of Scala's type system and its functional programming features. And I mentioned 3 ways that we can be typeful in this context, and I'm going to go into those in detail with examples later. Under the hood, this is not limited to pure Scala. So for reasons of performance, I wanted to, and also the fact that I didn't want to have to implement all of the operators myself, all of the ONNX operators. There are other pre-existing systems for doing this. They weren't really accessible from Java to begin with, and that was a separate effort underlying all of this. But there is an alternate project called Agate, which is somewhat newer than mine, which also does ONNX in Scala. There are a number of differences there, but one is that they implement their operators in pure Scala on the JVM. And they have more limited operator coverage as a result. But that's basically it. And then continuing on with the design goals. So I wanted to not just do the normal things that people do with ONNX, which is export it and import it from existing systems, or perhaps convert from the file format for one to the file format for another. Instead, what I actually kind of wanted to do was generate a domain-specific language for ONNX, and then that will be embedded in Scala, and we can just use it naturally as a Scala program, and it doesn't depend on any pre-existing frameworks or libraries. And there are other advantages to that too, which I will discuss later when we go into more detail. But as far as I know that this, and then, so we want to also generate programs from ONNX files in terms of that DSL that I was talking about. As far as I know, this is unique. Correct me if I'm wrong, someone let me know. But there are a lot of ONNX projects, I would say dozens at least, independent projects that integrate with or have some other form of ONNX support. Not many of them in the Scala and JVM space, but as far as I know, this is the only one that takes this direction with it. So then there's a supporting goal for this, which is ONNX on the JVM. When I started this, that was something that didn't exist. So I made it happen. I didn't write it all myself from scratch. I used a pre-existing project called Java CPP, and I built what it calls a preset to enable me to access native libraries, C++ libraries from the JVM. And then, so that exists now. There are a few options in the Java CPP presets for this. One of them is ONNX Runtime. ONNX Runtime is a Microsoft project, and it is pretty much becoming the de facto standard for running ONNX models. And it has a Java API. The Java API is experimental. It's not published yet where the Java CPP presets are. And, but that's also promising, the fact that we have any development in the JVM space outside of what I've been doing and what the Agate team have been doing on this. So, all right, those are the design goals. Now let's get into how do we actually use this. This is the quick start. And we're doing what I call black box execution here, because for efficiency and performance reasons, and for sake of simplicity, this is the first go-to. And if anyone was going to consider using this in any kind of a real world system or in production, I would definitely say that this is the way to approach it for now. So we pass the full model loaded from an ONNX file into the underlying backend. And that allows for full graph optimization because the entire graph is encoded. And so it can do things like combining certain nodes into other nodes. It's called fusion to make them more efficient. And it can do, it can tailor it to the hardware that it's working on and compile it into very efficient kernels for that hardware. So the end result is that we get what we were looking for. We get inference working in Scala. And if we want some extra type safety on top of that, we can do that. It can be type safe in the inputs and outputs in the ways that I'll describe later, but we need an extra source generation step. We can't just do this at runtime yet, pick up the file and run and have type safety because that's at runtime and we're doing the compilation at compile time. So we need an extra source generation step, but that's optional. And then in terms of performance, like I said, we do this partly because we want performance. So the performance is on par with ONNX runtime running from Python within 3% runtime. I didn't do a whole lot of detailed benchmarks yet, but very close. So finally, some code. This is where we see the 4-line quick start. The first line, actually, I guess I could have omitted, but the first line is we get the bytes from the ONNX file on disk. We read it into a byte array. Then we create an ORT, ONNX runtime model backend. And we do that by passing the bytes into it. Next, we create an input, a sample input. I'm calling it image tens here. You could imagine that this is your image of a potential plane. But in reality, it's just an array, a tensor with an array inside it, which is filled with the value of 42, a float with the value of 42 in for every element. And then that's just for the purposes of example. And then finally, the thing we really care about when we run the inference is the next line where we do squeezenet.fullModel and accept the image. And that gives us an output. And in this case, squeezenet is a neural network model for the ImageNet problem, which takes in images and classifies them into one of 1,000 categories, or depending on the posing of the problem, there may be a different number of categories. But in this case, it's 1,000 categories. And so the output is a tensor with an array inside it, and the values in that represent the probability for each of membership of each of those categories. So like I said, there are 1,000 of them, and we see below that the shape of the output is 1,000, essentially 1,000. And then we get the max, and that gives us 418 index max over that array, over the output values. And that tells us that in this case, the network is classifying it as 418, class 418, which is a ballpoint pen. And we didn't have a real input to this, but given that it was a bunch of 42s, sure, let's say that makes sense. But you could also do this with cats or dogs or planes or whatever it is that you want to classify images of. So that's it. That's the quick start. That's how to just embed it in your program and use it as a user. Behind that, as I mentioned, there are some backends, and the current default backend is based on Intel ngraph, which is a deep learning compiler and runtime. Using it here as an optimizing compiler, that's the graph optimization and the hardware optimization that I was talking about. Their implementation of ONNX is missing some operations. So that was part of the motivation for looking at other options. And ONNX runtime was also rising and making more steady releases and becoming the de facto standard in the interim. So then I started to add ONNX runtime support, and ONNX runtime claims 100% coverage of the operators that are included in ONNX. There's actually a scoreboard which shows all of the unit tests and the operator tests, and it shows that it's not quite at 100%, but it's very close and doing better in that regard than ngraph anyway. And that's currently working for the primary use case, for the black box use case. Another one that I'm considering is Deep Learning 4J, which is the deep learning library framework that Fabio was using in the preceding talk. I'm actually working right now with Conduit to integrate ONNX into another one of their projects. But then my next step is to look at importing ONNX graphs into Deep Learning 4J, and therefore I could also use that as a backend once I've done that work here. But that's speculative. Now before I go into detail about the rest of it, the fine-grained API, as I call it, the DSL, and the programs generated in terms of it, I'm just going to splash up one of those programs. Don't worry too much about the details of this. But like I said, this is still the same simple feed-forward neural network. You can see the image of the visualization on the top right. But the code shows you that it's relatively concise here. It's not as concise as you would get in something like Deep Learning 4J or a few other things, but it's relatively concise and readable in that we have inputs to our program. The input is the image. Well, in the other examples, it could be an image in this case. And then all of these things that say node learned, those are our parameters, the weights of the network. And then we have each of the nodes declared with their inputs and with some other optional attributes and things like that. But you can see that they line up. There's a transpose at the top, and its output goes into matmul, and et cetera, et cetera. That's it. I'll give other more concise examples after this where I can go into a little bit more detail. So the ONNX-Scala fine-grained API, as I said, it's still experimental. I'm still changing things about it. And basically moving forward, I've decided that I'm going to freeze development of this. This supports everything from Scala 2.11 up to .e, but I'm going to freeze development and just only support the full model API, the black box one, in Scala 2.11 and 2.12, and then in 2.13 and .e, primarily .e going forward, really. I'm going to work more on this fine-grained API. So it models that ONNX that we discussed as a Scala DSL. And it includes a minimal tensor type. It's really just, the most basic form is just a type alias over the data and the shape of the data. And with optional additional type safety that we'll discuss a little bit more. So the ONNX operations map to version numbered methods on traits, and they're stateless. These operations are stateless. They don't have any hidden internal parameters that could be changed or be different based upon training. Everything is inputs. So, and then the API itself is generated by another project that I have called ONNX Generator from ONNX via the Java CPP preset. It's generated from the spec and from the protobuf and from the C++ definitions, with minimal use of Scala meta, just basically to make sure that the source type checks and hopefully make sense. And then the ONNX graph isn't represented explicitly here. It's represented in terms of Scala control flow and in terms of normal Scala, essentially. It's a program in terms of this DSL. So let's look at just the operators, the operator definitions in Scala. There are lots of operators, like I mentioned. I'm going from simpler to more complex here, just a few examples. This is one of the simplest ones because it's a unary operator. It takes one input and gives you one output, and it's absolute value. That's what ABS is standing for here. And you can see here type constraints. That's the type T, is saying that absolute value operator only applies to certain kinds of data types, and those are these. And then we take the input X and then return a tuple because there may sometimes be multiple outputs. And then inside that is a tuple of 1 is the output, which is going to be element-wise application of absolute value. So, just converting your negative values to positive values over the entire tensor. The next example that I have is convolution. Again, was touched on in the previous talk because it's widely used and commonly used in convolutional neural networks, which are used for image processing tasks, classification and other image tasks. But basically you can see there's a whole lot more going on here, but there are a lot of optional things, which means there are defaults for it. So you can ignore, if you wanted to, just to get started with this, ignore all of those things up above and just look down to X, W, and B. Those are the actual inputs. Even B is optional because it's a bias here. But you have an input basically, which is X, and then you have the parameters or the weights, which is W, and that's it. You put it in and you get out convolutions over the tensor that you give it. And then this last one is one of the most complex of all of these things. It's called an LSTM, and it's one of those recurrent neural networks used in a lot of different contexts, but I've seen it applied in natural language processing a lot. And you can see that, again, there's a whole lot going on here. Some of it is optional. And there are 153 more of these operators. You can see the entire list. I linked it earlier. It's in the ONNX doc. And then how do we use this fine-grained API? We're not going to load the entire model all at once in this case. We're just going to instantiate this fine-grained backend, which I'm calling here backend all. In this case, I'm using the ngraph one instead of the ONNX runtime one to show that we have both of them, and the ONNX runtime one only works in the former case. So now instead of doing absolute value first, let's do square root. I didn't show you the output here, but it's going to do, again, the element-wise square root of that tensor. Now, I omitted the definition of long tens here, but let's just say that we made it with longs inside it instead of float. It's actually on the next slide, you'll see. But now it's with longs. We can pass an input, a tensor of longs, to absolute value, and that's fine. The input was negative, and now it's positive. You see right here, actually, I mixed up the slides a little bit or confused it, but long tens was negative. It applied to absolute value element-wise. Everything worked the way we wanted to. Now let's try to do the same thing with square root. We do it with long tens, we get a compile time error because it doesn't meet the type constraints because you can't, square root operation is not defined for long in ONNX. This is an example of the type safety that we can get from using this API. So then the next thing is that once we have this API defining the operators and stuff, how do we actually get generate a program that we can run that will execute the entire network by flowing through all of the nodes? So given a graph represented by an ONNX file, this time we don't just want to load it and run it. We want to produce the corresponding, hopefully functional and type safe Scala program. And the execution of each of these generated programs calls, like I said, each node or operation at the Scala level. So it's fine-grained. And then the downside of this is, like I said, the performance is not as great. There's overhead currently because of passing, data has to be copied to pass it into the underlying backends. And we also need to generate the ONNX proto for each of those operations. And then ngraph does some fancy compilation, which doesn't really apparently accomplish much when you're doing it at such a fine-grained level. Makes sense. So for a lot of reasons, it currently runs slower. It's faster than it used to be. With ONNX runtime, it looks like it's going to be within a factor of 2, which is not crazy. But sometimes it's been up to, with ngraph, for example, it's 10 times slower than the black box version of the equivalent, running the equivalent network. And there is currently a memory leak. I haven't tested this enough with ONNX runtime yet to find out. It may be a memory leak in ngraph, so something that can just be fixed by replacing it. All right, and then the generated models can be used for a variety of purposes currently. I have ideas of ways that we can do some fancy meta programming and macro things and manipulate these things at compile time in the future. But for now, what can they be used for? They can be used to ensure that you have type safety. For example, that you don't have an invalidly defined graph where some of the outputs are of a certain type and then the next thing that it's inputting to, that's being passed to, doesn't accept that type, for example. You can make sure that it compiles the generated version, and then you just having that peace of mind, I guess, you could go ahead and use the other one for performance purposes. You can use it for inspection if you just say aren't that familiar with Python or with the specific details of PyTorch or TensorFlow in Python, and you want to just look at it in relatively readable Scala. And you can also use it for modification, because there are some things that you might want to do only at training time and not inference time. There's also other ways that you can handle that, but you might want to make some minimal modifications to the model and then run it. So here's that absolute value operator again, except this time it's something called absnet. It's a graph with an input and an output, and that's it. And here's the generated program for it. Yeah, it should be pretty straightforward. The input data type and output data types are written there. You can see them. The fact that it's using list and for comprehensions here doesn't necessarily always make a lot of sense, but we can switch this for IO, and then we're lifted into an IO, and then we can use the for comprehension to flat map over those and compose them. So okay, here's where I think I have about 10 minutes left, so I'm going to really get into the typeful and functional highlights right here at the very end. So it's polymorphic or generic in the data type. Like I said, you can pass in any data type that you want, except subject to certain type constraints. And so I encoded those type constraints here. You may not have seen the union type notation. That's the vertical bar. But there's another much less readable way of encoding this in Scala 2, and I did that before. But you can see the type constraints here. You can see that you can use different types. That's it. That's pretty straightforward. And then the other two things are less common, even though sometimes this is not even like in things that are not as typeful, like in most cases in Python, even the data type is not included. But also these things are not generally included. Typed axis semantics, that is what is the meaning of each of the axes. So we don't accidentally, like say, index into the second axis thinking that it's the RGB channel, but actually it's a feature. Or anyway, we don't want to confuse batches with other dimensions, other axes of the data. And then the other thing that we might want to do with this is type shapes on our tensors, as in, for example, matrix multiplication. There's a constraint that one side of one matrix needs to be the same size as the other side of the matrix that you're multiplying it with. That's normally handled with throwing runtime errors in Python or other contexts. Or if you want to concatenate two different arrays together, for example, then their output size needs to be the addition of the sizes of the two inputs. And you can see here that we encode all of these things at a type level. And you can see that we get a tensor rank, and it accepts. So basically everything is encoded with sizes size 3, data channel is the semantic type of that axis, size 224, and etc. I have more details about this in the README, and you can see a lot of the examples of how you can get compile time errors from using the wrong sizes, or the wrong kinds of axes. But like I say here, op constraints are to do for both of these. So the groundwork is there, but that op constraint on matrix multiplication that I mentioned is not in place. Getting close to the end here. I've got under 10 minutes left. Functional highlights. The whole thing is stateless, referentially transparent, essentially, on the Scala side at least. There are mutable things happening under the hood in the native backend. But from our perspective of using this, and according to if those things are compliant with the ONNX spec, then they should be side effect free and stateless. So, and currently there's limited support. As I mentioned earlier, you can wrap this in an IO with a ZIO IO, or the entire API is wrapped in it, but it's limited support for that currently. And then another thing that's kind of important here is, like I said, that we don't have internal parameters that could potentially be stateful and change in the case of training. Instead, we pass everything in. We pass attributes in as inputs. We use default params where those are defaults. We pass in network weights params as inputs on each op invocation. So we could use this to continually update parameters in the network from training that's happening somewhere else. And we could be pulling it from a parameter server or off of a Kafka topic and a stream, or we could be doing it in the same process, updating it, but using some other technique for getting the new weights. And that's it. That's basically the whole thing so far. Like I said, I had a lot of other content. It would be nice to talk about differentiable programming and where we might go in that direction. That's going to be a whole different talk, I think. Keep your eyes open for that one. But for now, future work on ONNX-Scala. New backend. Since I wrote these slides, I actually have done the basic full model black box version of this for ONNX runtime, and it's working. I still need to do it for the fine-grained API. Continue to clean up and improve the usability of the API. I would love it if anyone can give me any feedback about ways that I could do that, things that seem a little bit awkward or could be done in a better way. I'm going to continue to build on new Scala language features. There are a whole bunch of features in Dotty that I have started to use and that I'm looking at using in improving this or whatever I do next even. Keep tracking ONNX. There's a new version of ONNX which was supposed to come out a day or two ago actually. And they're going to keep coming. So I need to keep updating this, including the API for the newer versions of ONNX. And then it would be really nice, maybe if outside of the scope of this, we had a standard typeful tensor type, like an ND array, something playing the central role that does in the Python ecosystem around these things. It currently doesn't exist. I have a few ideas for what that could be, but I would like to get collaboration and feedback from a lot of other people in order to make that something that can really gain traction and we can go forward with. So like I said, ONNX 1.7 is coming out soon. There's going to be a new version of ONNX runtime sometime soon. And these things are actually going to introduce support, limited support initially, for training. And it's going to do that by keeping the core graph, but augmenting and extending that graph with additional nodes to represent the calculation of gradients and to represent the weight updates. And so that's pretty interesting. And we can add that on, bolt that onto this potentially once it's actually released and supported by ONNX runtime. And then we can do training within ONNX-Scala as well. There's also other ways that we could approach doing the training, because like I said, all the params are input into things, so we can keep the params outside and do training in another way. And there's a lot of interesting approaches to automatic differentiation. Some of them have been addressed in Scala, and you can find links in the bonus talks section of my slides. I have more extra slides. But another thing that I'm considering is donating ONNX-Scala into the Linux Foundation for AI, which is where ONNX currently lives and a bunch of other ONNX-related projects. And I've had some contact with people from the ONNX steering committee about that. We'll see where that goes. And then related, this is not about ONNX-Scala particularly, but might have some implications for it. Like I said earlier, I'm doing some work with Conduit, the company behind Deep Learning 4J, and I'm hoping to make some improvements to the Scala API and other Scala parts of their ecosystem. And then maybe I can make use of some of that and the support for ONNX and Deep Learning 4J here in ONNX-Scala. And finally, like I said, I'd really like to go onward to fully differentiable functional programming with first-class language support, maybe eventually, which is happening in other areas, and doing this with Dotty. I think now is a very good time for us to start building on Dotty. It's starting to solidify, and it's a good time for us to start building the data science and machine learning ecosystem in Dotty, so that when it actually lands, we're ready to start running. And that's it. Contributions, users, funding, critique, anything, always welcome. Now I will take some questions.
May I ask a question?
Very sure.
As far as I understood, it's a framework for model training, yes? Overall, portable and compatible, agnostic by data format.
Yes, I mean, training happens, and then you typically export the trained model into ONNX.
Yes, and the question is, many times, as far as I know, data scientists, they are not experienced engineers, and for them, such complicated tools is quite hard to understand. What is the purpose of such a tool? To productionize data science models, or it is for data scientists by themselves?
Good question. Good question. I probably should have put that up at the top of the talk. But yeah, really my focus here is for productionizing this. And that's the core, especially the more performant black box form that I was talking about. And then also some things that are nice for data scientists in terms of the more fine-grained API and stuff. But really, like you said, the focus here entirely is on inference, deployment, and primarily production. And yes, there's still also gaps in the ecosystem in Scala on the other side of things, on the front end, where you're doing more exploratory work and developing the networks themselves and doing the training and stuff. Definitely some open territory in Scala for that, for anyone who is interested in that.
Okay, okay. Thank you very much. Thank you.
Thanks.
Question. You seem to use at specialized annotation. I thought it wasn't working in Scala in .E.
Yes, yeah, that is true. That's there as an artifact from the 2.x version, and also maybe it will be supported with some improvements in specialization. That's one of the .E features that I'm looking for, but it doesn't seem that there's been much activity on it recently. But yeah, auto specialization is supposed to be there in .E, so you're right. That was not necessary.
Okay, thanks.
Thanks.
May I ask a question?
Sure. Yeah.
You said you worked with R. Do you have any experience with working with R when dataset is not fed into RAM? Because it's common for data scientists to work with a lot of RAM on their notebooks or PCs, and everything is fine while everything fits into RAM of computer. But if the data set is very huge, like weather prediction,
Yeah.
What could you do in R stack? What are the options?
Yeah, so like I said earlier, I don't really use R a whole lot, but I do know that R has an interface to Spark, or Spark. Anyway, there's an R interface for Spark, and so like if that was really a problem that I was tasked with, that would be the first go-to, because I'm already very familiar with Spark, and as I understand it, I mean the Python interface for Spark is more limited than the Scala one, and the R one even more so. So it's lagging behind a few releases. You may be missing some of the recent features that you might find useful or want, but really that would probably be the lowest barrier to entry for me, at least, and I think for a lot of people, given the amount of Spark knowledge and expertise and documentation and stuff that there is out there. In general, I mean, in R and beyond, I'm interested in what the next sort of big thing for distributed compute is going to be. So Spark is getting relatively old now, and their release cycle is getting very slow, and I don't think they're going to make any deep fundamental changes to it at this point. They're going into 3.0. One project that I'm aware of that's kind of interesting is Unison, made by some major figures in the Scala community, formerly or currently possibly, but anyway, people with a lot of functional programming experience, people who wrote the book or wrote some of the books in the Scala functional programming world, and they're working on a language that is inherently distributed, essentially, on one that encodes remote workers and where you can shuffle around work between them, and hopefully eventually be as transparent and easy to use as Spark, but very much functional and built on Haskell and everything.
Well, definitely check out Unison. Thank you.
Yeah, I haven't dug in deep to it myself. It's a very early stage, but they've been working on it for a few years at this point. It's certainly usable, but it's not production ready. I wouldn't say, but don't take my word for it. I'm not an expert. Look into it.
Well, just the ideas, could be very interesting.
Yeah, for sure, for sure. I'm constantly looking at new things, which may not really be super solid, or maybe even abandoned, or just emerging themselves, and looking to kind of harvest ideas from them and incorporate them into what I'm doing. About ONNX-Scala. So I haven't dug super deeply into it yet, but like I was saying, training is one thing that's missing from ONNX-Scala. And I just sat in on an ONNX community meetup workshop yesterday, which was, I don't think probably had anyone else attending who was focused on Scala in the way that I am, but there were 200 attendees from all over the world and different industries and stuff. And there was a lot of discussion about the training implementation in ONNX, which is coming hopefully next week or the week after to being delivered in a release, but it's already there in master. But it's sort of just building blocks for a training system. So as far as I understood it, they don't implement the gradients for all the operators in ONNX yet, which means that you can't even practically use it it's sort of just the framework. They're laying the framework and then the groundwork, I mean. And then the next release, which is going to be quite a while away, there will be some more support for that. And we also need to have support for that in ONNX runtime. But a different approach that I've been looking at is doing automatic differentiation myself, which a number of different projects in Scala have done. We've had a little bit of discussion around it in a machine learning for Scala Gitter group that I made, and a bunch of people have done projects based on automatic differentiation. I'm looking at one of the newest approaches to automatic differentiation, which is source-to-source transformation, or source code transformation. And I think that there's a lot of interesting opportunities for using Dotty there, using the Dotty macro system to, get the code in form of expressions and be able to manipulate it. Maybe it might be necessary to use Tasty and full ASTs, but otherwise just possibly Dotty macros to do transformation, and then take the ONNX graphs that are currently only used for prediction and add automatic differentiation capabilities to them and make it actually able to learn, even if we don't have the ONNX training support there yet. And also Dotty is also really promising for, so there's two different approaches that I discussed in the ONNX-Scala talk, and one of them is just taking the model and running with it and running it on the back end. That one has to be done at runtime because you don't have the model at compile time necessarily. So in that case, we could maybe do some staging, which Dotty introduces, and then we can generate the code like I did currently in ONNX-Scala, except generate it and compile it and use it all at runtime using staging. So on both sides of the compile time and the runtime side of the Dotty metaprogramming thing, I'm looking at ways that could be potentially useful. Yeah, in the training side, on the macro side, that means that we could just take like I said, an inference function and then compile it, and then as a user of that compiled artifact, then you can just call training capabilities because they were generated. Yeah.
For training, we need to put it into GPU, so we need. So we need compiler to C code, which will fit into GPU eventually. Yes.
To CUDA, well, yes, but that's at a lower level. I'm not working with CUDA explicitly. I have in the past, but I'm not like dealing with CUDA kernels or any of that low-level stuff explicitly. Currently, I'm using ngraph and ONNX runtime, both of which have support to varying degrees for GPUs. So currently, it's not built into ONNX-Scala, but in theory, it should be as simple as just going in the dependencies in the build.sbt and changing it. Well, no, maybe not for ONNX runtime or ngraph. For other Java CPP presets, you can just change CPU to GPU in the dependency, and then hopefully it should just drop in work. In this case, you maybe just have to set a setting, make sure that ONNX runtime is built with GPU support, which is something that I'm going to do, but I haven't built into the preset yet. And then you just need to flip a configuration switch to tell it to run in GPU mode or something like that. Yeah.
Okay.
Alex, one more question. Could you share your opinion on new TensorFlow and the fact that Google chose Swift as the main language for implementation?
I didn't hear the first part. I heard Google, TensorFlow, and Swift.
The new version of TensorFlow will be implemented at Swift. What do you think about this? Sorry.
Yeah, so I've been looking into that too. I also just pasted in a link about Swift for TensorFlow into that Gitter channel I was talking about. I haven't dug into it super deeply yet, but as far as I understand, it's not quite what you said. It's not that they're re-implementing TensorFlow in Swift. It's that they added first-class Swift language support for automatic differentiation, which is what I was talking about with the source code transformation, where you can just write normal Swift code, or maybe like with an annotation here and there to tell it that you wanted to do exactly what I was describing and generate gradients and stuff like that automatically and do automatic differentiation. And then that has an integration, a very tight integration with TensorFlow. So that's why it's called Swift for TensorFlow, because it's using Swift as a front end to access TensorFlow, and the really heavy operations and the network definition and everything else can be done in terms of TensorFlow, and then the execution is delegated to TensorFlow. So I think it's much more about Swift as a front end and as an improved user experience with first-class automatic differentiation support, making it kind of differentiable programming, where you can just write code the way that you normally would and throw some annotations in there, and then have TensorFlow learn. But those automatic differentiation capabilities also work outside of TensorFlow in Swift. If you just write some manual code yourself, as long as it's in terms of the operations that are supported in Swift, then it will work. Yeah.
Thank you.
Similar concepts and projects to that, which I think are kind of on the cutting edge. And the Swift for TensorFlow one is the biggest one, I think, because it has Google behind it and the name of TensorFlow behind it and everything like that. But there are a few others. There's one in the Julia ecosystem called Zygote, which works with a machine learning library called Flux. And it also offers very high-level support for these things. And Mia is another one, which is Python-based, but it has its own internal representation, so they intend to support other languages as front ends. And I think that I'm planning to advocate to those guys and try to get Scala at the top of the list for a next front end after Python. But that's a similar kind of case where it supports a subset of Python, but still a relatively general subset that can do things like controlled flow and recursion and higher order functions and things like that. And then it transforms that source into its own internal representation and then is able to do some nice automatic differentiation on there.
The question was that it is hard to explain Scala to data scientists, because data scientists, because it is they not focus on language.
They prefer Python, right?
Yeah, I think so. The main connection point for data scientists in the Scala world is Spark and Spark ML and the data frame in Spark, and a lot of those things offer touch points for people who have experience in the Python world. So it makes for a relatively easy point of transition, and Spark itself has Python support, of course. But Vladimir, you mentioned to me that you primarily use R. Is that right?
Yes, that's right.
Yeah, is that how many of the rest of you commonly use R?
I use R time from time.
Nice. I think I would say that's probably the second point of origin for people coming into the Scala community looking at these things, and the second most popular in general, most likely. Myself, I haven't really touched R in a long time. I use Python a lot more regularly than I do ever touch anything with R.
My question is, I saw there was news about quantum computing and AI. Have you heard of the subject?
I've heard of it. It's not something, I mean, I remember touching on that in university quite a while ago. And also being aware of, I think the company is called D-Wave. There's some specialized hardware producers that produce very expensive quantum computers, and Google and NASA, et cetera, have them. I remember looking at a job posting once for them years ago. They were looking for someone specialized in Python to try to bridge the gap between their hardware and real world developers on these things. But in the intervening years since, occasionally, of course, quantum computing is always on the, something that's coming up and is going to be important for all of us in general. But I haven't seen any projects recently that really caught my attention that were doing any sort of application of quantum computing to machine learning. I'd be interested if you have any links or if anyone else doesn't know of that kind of work.
I don't have a question as much as I have a comment. What your talk is about is very interesting to me, because I work at AccuWeather. We process a lot of weather data. Mm-hmm. And we also have a machine learning initiative. And we recently hired a data scientist who, he hasn't even joined us, he's joining on Monday, I think. But my understanding is he knows R really well. but he has no idea just how much data we have. And when he sees that data and he tries to process it with R, he'll probably come to us with some questions. So I'm looking at what you're doing and I'm thinking, you know, maybe using what you're doing, we can help him with his scale problems because he's going to have them. But
Sure.
you know, it'll be a while. He's just going to be starting out, and he's starting out remote because, of course, we're all working from home at the moment, and it's going to take some months for things to really get going. But it won't. I don't know. There are ambitious timelines that I don't know how they're going to. He's responsible for the AI component of something that we're doing. Mm-hmm. I'm responsible for some other components that are before and after that can run simultaneously. And but I'm curious how he's going to approach the AI aspects of it, because I have an AI background that's not really data science as much. You know, these days we're into machine learning and data science. But for example, I was almost Marvin Minsky's grad student in 1986. And he tried to convince me to be his grad student, and I told him I didn't think I was smart enough to be his grad student. And then he tried to convince me that his research said that nobody was more than twice as smart as anyone else, but I wasn't buying it. And unfortunately, it was during AI winter, if you remember that. But
yes.
But anyway, he was a really nice person, and I've kicked myself ever since. I mean, I'm still friends with a lot of MIT people, but anyway, you know, what you're doing to me is very interesting and may intersect what our new machine learning guy is going to have to do. We'll just have to see. I'm definitely going to show it to him, and we'll see what happens.
Sure, nice. That's good to hear. Good to hear. Yeah, I think if you're talking about really implementing an entire system, right now, what I did with ONNX-Scala is, as I mentioned in the talk, it's a relatively limited scope component of that because it doesn't include training. So that's really necessary, unless you're just doing something where you're totally applying something out of the box, like an ImageNet image classifier or something, which really a very small proportion of real world machine learning problems fall into that category. Then you're going to have to at least do some training. It's possible that you're building on pre-existing models, and then you're doing something like transfer learning. You have a model, and then you're going to fine tune it or specialize it to your particular use case or your particular data set of images in the ImageNet case. But AccuWeather, that's interesting. Yeah, you're not going to find any off the shelf, you know, ready to use models that are going to be even close to applicable for you in that domain.
Well, I'll give you an example. So a few years ago, Microsoft, a guy at Microsoft came to us and he said, I think it was just a toy example. He wanted to see how well he could predict the weather tomorrow based on the weather today, given that most of the time they're very similar. And I remember thinking, God, this sounds awful, because that's not what weather prediction should be. It should be based on a physics model of the atmosphere and fluid dynamics and all that stuff, you know, and that's why now 3-day forecasts are very, very accurate, and 7-day forecasts are now as accurate as, you know, 3- and 5-day forecasts used to be, is because the science has gotten better. But there still is this force in the universe that wants us to do more prediction using AI and machine learning, and how that interfaces with the science and the physics behind, you know, and chaos theory and all that. To me, it's very interesting. You know, we've got these different, you know, in that you have your functional and your imperative people at battle, you have your scientists and your machine learning, pure machine learning people saying, well, maybe we can do what you're doing without the science. And I'm like, oh God, but yeah, but they're playing, they're doing experiments. And maybe, you know, and one of the things about machine learning is you discover things that you didn't expect to discover. And I think that's really what they're looking for.
Yeah, definitely. It sounds like a very similar experience to what researchers in computer vision and natural language processing have experienced over the recent years of the explosion of deep learning and its successes. And that's not to say that those people and their knowledge doesn't have any role. It definitely has in real world serious computer vision systems, for example, the kind that they're deploying in self-driving cars. There still are significant components that have had a lot of human engineering going into them, but they're working synergistically with the deep learning approach. And in some cases, yes, like in image recognition, in speech synthesis, there are large portions of pre-existing systems that have been popped out and replaced entirely as a module with deep learning. You can't do that in every case, and even in seriously complex systems, you still need a lot of engineering knowledge to glue it together and to fit it into the context of the overall pipeline and business problem and everything else. But yeah, I think the future really is about collaboration between domain specialists and, like you said, those people who really deeply know the science, and then practitioners of machine learning like me, who doesn't know much about weather science or vehicular science or whatever, whatever it might be domain that we're talking about, unless I have worked on it and touched on it in the past. Then it's about collaboration and building something that takes advantage of both skill sets.
One thing that just occurred to me when you were talking was, so one of the things that we want to do at AccuWeather is when there are storms, we want to warn people, especially tornadoes or severe thunderstorms, tsunamis, things like that. We want to save people's lives if we can. I mean, so does everyone in the weather industry. But, because we're competitive, we try to do it before other people if we can. And tornado season is coming up in the US. It's kind of already started. And, but there are behaviors of people on the ground that, we actually have some data from people's AccuWeather apps. We know where they are, but we don't know who they are. So internally, we were able to map what's going on in parts of the world with coronavirus based on how often they were asking for the weather and where they were asking for the weather from. And we didn't know, okay, should we present this to the world or would they freak out for privacy reasons? Because we're really not tracking who people are. We're just, we know where the API requests are coming from. And it occurred to me that if you have a tornado coming through and you can see how dots are moving on a map, whether people are actually in danger. And maybe you could use machine learning to try to anticipate things that people are about to do that will get themselves killed, so that we can make sure that they get the warning the tornado's coming right for them. I don't know, just random thought off the top of my head.
Yeah, interesting. That one I can kind of see as a ranking problem. I do a lot of work on recommender systems, and in that case, it's about ranking, and getting the best results in the top N. In this case, you could frame it as a similar kind of problem where all of your users need to be ranked in order of, priority for some kind of intervention or whatever extreme weather event, like you said, that is likely to come towards them. And then you just have some kind of a cutoff level, because the thing is, yes, in theory, you could alert everyone. You could, if you have access to the systems, you could send SMS emergency alerts to every phone in the US, but it might be better to take a much more targeted approach like what you're describing. And then you just need to have a defined cutoff and take only those who really rank in the danger zone, sort of.
Yeah, I mean, actually, you just gave me an idea that I can give to the AccuWeather people. So, for example, right now, when a tornado is coming, we give alerts, but we give alerts. We give the same alerts that the government gives. It's just we're proud of the fact that we get the alerts to our customers. We get the weather services alerts to the customers faster than the weather service does. Okay, I mean they're giving us the data in real time, but somehow their mechanism for the public works slower than us just getting it from the weather service and telling our customers immediately. Like it's, we get it out within like 20 milliseconds. We have several systems and we watch them race, and the one that wins gets extra RAM the next time we have an upgrade or something like that. But, or maybe the losing one should get extra RAM. But we also have this product which we sell, which is, it's for large plants. So if a tornado is coming and you have a manufacturing plant, You see, the weather service will tell you you have a tornado in your county, but they won't say exactly where it's going. Whereas we have meteorologists who are actually looking right at everything, and they know exactly where it's going. So we will warn people who have our service, you don't have to shut down that because it's not your factory, because it's not coming to you, or you do have to shut down because it's coming right for you. And for the factories, it's $1 million decision one way or another, whether they shut down or not. So like every, I don't know if you ever watched John Oliver. This week, okay. So he did a kind of a hit piece on AccuWeather in October, because like 15 years ago, AccuWeather was behind an effort to do some privatization of things the National Weather Service does, which I remember I thought that was a bad idea. You know, I like things being as public as possible. And for the private companies to just do added value, let's put it that way. But John Oliver, most of it was pretty funny. Our management thought it was pretty funny, even though it was kind of a hit piece. But one of the things that John Oliver did, which was kind of unfair, was he said that, our president was quoted as saying, if so-and-so town in Illinois had a contract with us, we could have warned them and saved lives. And John Oliver's like, what? You didn't warn them? And what John Oliver didn't say, because maybe he didn't know, is we are prohibited from warning people, for telling them anything different than what the government tells us. It's like when we give weather around the world, we have to adhere to the local government, like China, air quality, okay? We have better air quality readings than they do, but China insists that we use theirs, okay? Because that's China. And so anyway, with the US government, it's the same thing. We cannot warn people, we cannot warn the public in a way that is different than what the government did. Unless they have a special contract with us, then we can do whatever we want. And that's what John Oliver got wrong. But
significant regulatory issues there.
We have our mobile app, right? And if someone paid an extra $1 for their mobile app, then we could actually give them a specific warning similar to what we give anyway. So you gave me a product idea, whether you realize it or not.
Okay.
I should give you commission if they buy it.
Great. Well, yeah, I hope that works out for you. Thanks everyone for showing up. Interesting conversation. If anyone wants to continue it offline, just contact me.
Yes. Okay.
Thank you very much, Alex. Bye. Bye.
Thanks everyone.